So what we're going to do today is we're going to look at Python and also kind of give you an introduction to very basic Python programming just to get you started. This is not by any means a full course or even a kind of an in-depth Python programming review. Mostly I'm going to show you how to use a Jupyter Notebook, which we'll see what it is in a minute, and some very basic kind of Python syntax. The rest, as you go along, you'll have to kind of either you already know it or you'll have to figure it out yourselves, either through watching other videos online or asking chat assistants, etc. Okay, so like I said, we're going to use Python and we're going to use 4 other libraries. Those are NumPy, Pandas, Matplotlib, and SciPy. NumPy is for numerical computing. Pandas is for data management, so to build tables and to kind of manipulate tables of data, especially when you have big tables with a lot of columns and a lot of rows. You can think of it like a programmatic Excel, where you kind of manipulate the columns and rows like you want. Matplotlib is the plotting and visualization library. And finally, we have SciPy, which has kind of scientific functions and statistic analysis. So what I'm going to do is start by talking about Google Colab, which is kind of Google's, if you go to google.colab.com, actually its full address is Google colabresearch.google.com, but if you just say colab.google.com, it will just send you there, and you'll get something like this. And you can get you can create a new notebook, and you need a Google account, but it doesn't have to be any paid account. Any free account automatically gets Colab. So let's say new notebook, and then you get a Google notebook. Depending on your connection speed and the servers, there might be some lag, and you can actually change the name of the notebook. So let's call this my first notebook. Actually, let's put spaces in there as well, at least underscore. Right. So now you have the notebook here. Okay. So now in a notebook, we can have 2 types of cells. A notebook is made up of cells. So whenever kind of you're building up the notebook, you can have cells of code where you can kind of put in Python code, or depending on your usage, it could be kind of R code or Julia code as well. And you can delete these cells, and you can also kind of see shortcut for that. You can press this little garbage can to delete a cell, or you can just go Control M and D will delete. Adding a new cell is Control M and B, or you can add a text cell. So what's the difference between a code cell and a text cell? Let's delete this as well. Delete this as well, and let's start with a text cell. You just add a text cell. It's basically a cell where you can enter text. So a notebook is a kind of a mixture of code and text you write. So let's say we can say here we start, say, getting started with, let's say, Python. And once you kind of close this, you'll get this text said getting started for Python. You can actually format this text, so you can go here and say, for example, make it a new section, right? So instead of new section, if I put my text here, and this kind of the first level section headers are basically hash mark and then a space, and then you enter your text, which will give you kind of the a title, right? And when you close, this will have a nice title. And the good thing is you'll also get kind of this section header here. Okay. And after the section header, you can just kind of write normal body text can go here, blah, blah, right? And so you can have a heading, some normal text, and you can just write the whole paragraph here. And you can kind of do separate things, make certain parts bold, italic, what have you. And you can do it through the toolbar here, or this whole thing uses format called Markdown. And you can see it's very kind of easy to learn, actually. Let's see, where do we have? Oh no, that's not the one. Cheat sheet, yeah, there we go. So, like we said before, headings can be single hash, double hash, second order heading, three hashes, third order heading. To make some text bold, you just put 2 asterisks on each side. To make it italic, you put 2 stars on each side. If you put a kind of a thing here, you can make a quote. So if you put a less than sign here, say this is a quote, so kind of like an email, right? And it will appear like kind of inset and separately. You can put in kind of verbatim text so that the formatting is not changed really, right? So close this. So this would be kind of like this, right? So it's just like you entered it. It keeps all the spacing, etc. Other stuff you can do is you can have horizontal rules. For example, if you just put 2 kind of 3 hyphens, you get a nice separator line here. And other stuff, right? You can add images, you can make links. Links are pretty useful. So if you say so let's say let's have a link to Metu, and that will be https www.metu.edu.tr would basically be a link. So when you just say Metu, it will, well, Google is warning you that you're leaving the site, but it basically sends you to Metu, right? So you can have links, etc. One other thing we can have here is also equations. So you can have something like, it has its own language, but it works pretty fine, right? Let's actually these all in the same line. Yeah, so you can have kind of, this is LaTeX math, so you can search for it online, LaTeX math, and here's kind of ways, this gives you a kind of a guide of how to write math in LaTeX if you want. Might not be very necessary for this course, but it's useful to know. The good thing about this is basically you can write a whole paper with this, or a whole homework, right? So you write the text, every now and then within the text sections you put code sections. So the code sections will just have, in this case, Python, in our case Python, but otherwise it might be something else. So here I might say, for example, very simply, put some Python code, and right now nothing's working yet. Notice this connect is not connected yet. You can connect to kind of a hosted runtime, which is basically a small computer that will run your code, but you don't have to do anything directly. The first time you run your first code cell, notice that it will automatically connect to something that will run that code by kind of by default. That will be Python. So for example, the print hello world command actually produced hello world. So this is now a text cell. This is a code cell. Here's another code cell. For example, we might say, let's add 1, 2, 3 plus 3, 4, 5, and it comes out with the answer. So whenever you run a code cell, whenever you run a text cell, you're basically you edit it, and when you run the cell, you'll get formatted text. For a code cell, when you run it, the code runs and you get the output. Whether that output is text, whether that output isn't anything. For example, if I take this instead and say some variable is 1, 2, 3, notice that it doesn't output anything. This code runs, but it doesn't have any output, so it doesn't say anything. But right now, if you look at, let's see, data inspector and reload. Oh, that's only works for data frames. So anyway, so now there is a variable called x here. So if I take a look at an x later on, I know that it's 1, 2, 3 because now it has output, right? So the way you run these is you can press this little play thing here, right? Or again, the shortcut is Command Enter. So for example, if I say hello world, hi, and then without ever kind of pressing this play, if I say Command Enter here, it just directly runs this piece of code. So I don't have to move my mouse all over the place to there. By the way, you should be seeing kind of down here any kind of keyboard shortcuts that I enter throughout this course. Okay, so that's essentially what Jupyter is. And like I said, once you run your first code thing, you'll get a machine which has which has kind of a very simple machine, but it's not that bad. It has 107 gigabytes of disk, 12 gigabytes of kind of RAM, and if you actually pay for it, you can get better machines. But for our course, you don't need that. Free one is just it's fine, right? Because we're not going to run code that's going to need GPUs or anything. You can, for your own use, if you want to use this later on, you can have different runtimes with, for example, you can use Python like we are right now. You can have a R runtime or a Julia runtime. R might be useful. And you can have a CPU instance like we have here, which is just enough for us. But if you're doing some machine learning course or etc., you might want a GPU, and the free subscription gives you these two, either GPU or TPU. But if you have a paid subscription, you can get bigger GPUs, etc. But that doesn't really concern us. Just a basic Python runtime is fine for our course. So these are all done, and the good thing about the kind of the Google Colab environment is that you can actually have all the libraries that we need already installed. So for example, later on we're going to use maybe NumPy or Matplotlib, let's say, right, which is the plotting library. And when we run it, it directly imports because Colab already has that, right? So actually, let's say pyplot. And the good thing is it also has autocomplete, so if there's something can be completed, say plt, and here if I say plt, did I run this? Plot, let's say 1, 2, 3, 4, 5 against 1, 2, 3, 4, 5. So we should get it just a line, right? So you get the plot. So output doesn't just have to be text like this. If your function outputs a graph, you'll get a graph as the output. And that kind of makes the whole notebook thing very useful. As you can see, you can kind of write a bunch of text and then have your figure here generated by code. And the good thing is the code that generated that figure, which means all of your work is already in the notebook. Therefore, you don't have to redo it, right? And whoever you give this kind of notebook to can take the notebook and rerun it and get the same kind of graph, which leads to reproducible research, in your case, reproducible homeworks and assignments. And you can show and hide the output if you want, etc. And again, you have kind of each heading creates a section here in this table of contents of the notebook. Therefore, if I go with another kind of section, let's say I have a new section now. Let's put a text area here, say Python fundamentals. And let me just make that a top level heading. And I press Command Enter or Shift Enter. And now you see I have this thing. Now I'm going to get rid of these because I don't want them to cause problems. And remember, the delete was Command M or Control M if you're on Windows, D. So we'll get rid of those. We'll write more of those in a minute. And we'll just say here, for example, we'll get rid of all of this junk as well, so we get a nice notebook. We'll say Jupyter Notebooks, Colab, and scientific Python. So now you have this, and we'll start with Python fundamentals. So you get the table of contents here. Let's also kind of put, what do we do? There we are. And we'll say, for example, here, libraries covered are going to be NumPy, SciPy, Matplotlib, and what was the last one? Pandas. Right. And I don't want this italic, I want it bold, so I'll do it like this. Now we have kind of a beginning, now we have the Python fundamentals cell. So let's talk about Python fundamentals. Like I kind of showed you one thing before. The easiest function you have is print, and you can give it anything within parentheses, kind of in quotes, and that will basically print that to screen. That's the first thing you do in any programming language, kind of try and go print hello world to screen. And with Python, it's very straightforward, just say print and whatever. The good thing is you can do several things. So you can say, for example, hello as a string and then put a comma and say from and put a comma and let's say Python, right? So if I write that, the first one prints hello world, the second one, notice it took these three strings and it combined them with spaces. And you can kind of, the spaces are assumed. The things it combines doesn't have to be strings. Okay, Okay, so it's offering AI-powered autocomplete for me. Yeah, I'm not going to do it for now, but if you want, you can use it. You can do, for example, something like, what if I say 1 plus 1 is a string, and let's say I run this, I get 1 plus 1 equals, this part obviously is a string, and if I say comma and actually write 1 plus 1 here, what it will do is it will take the string, it will calculate this value and add that to the string and print it, so you get 1 plus 1 equal to 2, which is kind of makes sense. So what else can we do with Python? Some kind of very simple stuff. Let's talk about variables and data types. So one thing you have to know is Python is dynamic, so you don't have to declare let's make this data types beforehand. So some programming languages will require that. So you have to say, for example, if x is a variable, x is going to be a number, or x is going to be something like a string. In Python, you don't need that, but you can basically, let me just, to save time, copy and paste a bunch of different variables here into this thing, and let's go over them. So obviously you can have integers, which are whole numbers, something like age, and you can say 25. But in Python, I don't really say, I can say age is an integer, but I don't have to. If I give it an integer, Python basically assumes that age is going to be an integer. And later on, I can change it to something else, like a string, and Python will just accept that as changed. And then you have floats, which are kind of decimal numbers. And for example, even if your thing is a kind of a integer, if you put a dot after the integer without anything following it, Python will consider that as a float. Well, it's the same thing as saying 36 dot is the same thing as saying 36.0, right? Strings we already saw. Things, for example, a name might be Alice, a greeting might be hello world. By the way, you can use both types of quotes, single quotes or double quotes. The good thing is, for example, if you're using double quotes, you can say Alice is something and use a double quote within that, and Python will understand that the quote is not done yet because you started with a double quote. Same thing here. If I use a single quote in the middle of this, it will think that the quote is finished early, but if I use a double quote in the middle of it, it just becomes part of the string. So you can use either one. There's booleans, so true and false type variables, and those are given values either true or false, and they have to start with uppercase, so be careful about that. Something like if somebody is a student, his student would be true, otherwise false. And you can print them out like we did before. So print name and then a string is, and then the age and years old will basically say if name is Alice, it will substitute Alice here is 25 years old. Temperature is that temperature. Student question mark will say true. And you can actually use the type function and give it any variable, and it will give you the type of that variable. So let's run this. So just like we thought, Alice is 25 years old, temperature is 36.6, student is true, and then notice that it wrote as age, type is integer, temperatures type is float, etc. And notice that if I put the dot here, like I said before, and if I rerun it, Now age, it thinks it's float as well. Although it's an integer, it's taken as a float if it has a dot in it. So that's variables and data types. Some more complicated types are collections. So let's have a new section for those collections, which will be lists and dictionaries. All right. So lists and dictionaries are, let me actually copy this whole thing from here. So lists are ordered, so they go 1, 2, 3 collections. So it has a first, second, and third, and so on and so forth. Dictionaries are not ordered by numbers, but they are kind of maps from one thing to another thing. It makes more sense if we actually take a look at those. So let's take a look at lists first. So for example, a bunch of ordered things might be grades. The list of grades of people. First grade was 85, second grade was 92, third grade was 78, 95, 88, and so forth. And let's say you might have a list of fruits. The first fruit is apple, banana, then cherry. The only interesting thing about kind of this is Python is zero index, meaning the first thing in the list will be item number 0, right? So the first element is 85 here. It's going to be actually item number 0. Item number 1 is going to be 92. Item number 2 is going to be 93. So the list goes on to, if there's 5 things in the list is indexed from 0 up to 4. And the minus first is going backwards. So minus 1 is 88, minus 2 is 95, minus 3 is 78, and so on and so forth. So you can kind of get individual parts of the list by giving the index within square brackets. And then you can take whole slices of the list as well. So you can say, get me the grades list, but starting from 1 up to, but not including 3. So remember, this is 0, this is 1, this is 2, this is 3, 1 up to, but not including 3, so you'll get 92 and 78. You can change lists, so the original grades was like this. If you say append, it will actually change this in place and add 91 to the end. If you sort them, it will sort the list based on either if it's strings, it will sort alphabetically, and so on and so forth. Let's actually put another print here. Print grades. And let's say after append. So it will print grades several times. So actually, let's say also here, let's take that and say before append, write grades, and then add 91 to the end, and then give me what it looks like after the append, then sort and give me what it sort. And finally, len for any collection gives you the length of that collection, right? So if we run it, yeah, so it got 85, which is a 0 thing, remember? Minus 1 is the last thing from the back. You can get ranges, and before append is the original list we gave. We add 91, and then we sort it, and then we print it again as sorted, so it goes in sorted order. By the way, you can go and say sort. You can kind of sort descending order, so you can basically say here reverse true. So reverse true. Notice that here it goes from small to large. If I do reverse true, now it goes from large to small. So you can actually put switches into these functions. And finally, len, like I said, gives you the count of. So that's lists. And for dictionaries, they are kind of like lists, but they are made up of kind of name value pairs, right? Key values. So, for example, a dictionary could be represent a student. So the name maps to Alice, age maps to 25, grades maps to this list. And I use it just like an array. I say student. Instead of, for example, give me the first thing, I say give me name, and it will give me back Alice. I say give me the email, or sorry, initially there is no email in the student kind of dictionary, but I can add one. So if I give a new key, if I give an existing key and say equals something else, that key will be changed. If I give it kind of a non-existent key, that key will be added, right? So if I run this, for example, you get the original student, it prints out the name, so that's this line, and then I create a new key called email, and for example, email I give Alice at uni. If I print the student dictionary again, notice that now it has this email thing, which means I can then say, for example, student email Oh yeah, there you go. The thing with Colab is, one thing is sometimes due to the internet, it might kind of seem like it's stuck because it can't make a connection or there's lag, but otherwise it should work. You generally, okay, I want to generate with AI. By the way, you can use generate with AI if you want. I'm just trying to keep it close so that it doesn't confuse us at this point. So normally, if the connection is good, you should get these autocompletes and everything. If you're not getting it, maybe there's a slight disconnection at that point. Okay, so that's dictionaries. Next thing I want to talk about is control flow and loops, etc. So let's add that as a section. Why are my sections not as deep as before? Actually, let's make these all the same depth so that they look nice on the thing. Yeah. So these will all be, under Python fundamentals, so that you can actually fold these, right? If I fold them, I get rid of all of the Python fundamentals. If I fold variables, I just get kind of fold that part. So control flow, conditionals and loops. So one thing you have to be careful about Python is that it uses indentation. Oops, close that. It uses indentation. So how far in a piece of code is to delineate that code as part of a block. So here's one example. So if you have the if statement, for example, you can say, let's say score is 85, and I want to ask if score is greater than 90, grade is A. If else if, so if this is not true, jump to the next one. If score is greater than 80, grade is B. Else, if that's not true, go to that. And finally, if none of them are true, say grade is F. And notice that these are kind of inset by a certain amount, in this case 4 spaces, and that's fairly standard, 4 space indent. That basically says if this is true, if this condition is true, if score is greater than 90, do everything within this block, and the block is defined by the fact that it's indented. So if I run this, you say finally it prints kind of score, and then within, by the way, this is what's called an F string. So you can build a template string, right? Saying whatever you want to write, and then within kind of curly braces, you can put outside variables. So Python will plug them in and create the string and print it. So the way you do that is write a normal string. If I don't put this F here, notice what's going to happen is it's going to write the template string. Score, put score here, grade is equal to grade, put grade here. It doesn't actually put those things, but if I put an F in front of the string, notice that the syntax highlighting changes as well. It basically embeds those variables, so score from the outside and grade from the outside, into here, right? So you get score 85, grade B. And now, just to show you what these blocks mean, I can actually go in here and say print, for example, make something like this. Okay. And actually, C is not okay. C is meh. B is okay. And print F is right? Notice that when this print is in the same order, kind of the same horizontal level as grade, it's indented. Whenever score is greater than 90, Python will execute this line and also execute that line. So for example, here it will just go in, set the grade to B, print OK, and come out. So if I set the score to 5, for example, and then you'll get and the score is 5, its grade is F, and so on and so forth. Right? One thing you can't do is, for example, if this last print was outside here, whatever you do, it will print the O because it's no longer part of this else anymore. It's a separate line like this one, which means it will work. You can't do that obviously in the middle. You'll get an error saying invalid syntax because the score suddenly, there's an else if where there was no if, because once you made this come out outside the print OK, you ended this if else thing. So it says you can't start with a new elif, and you'll get that before you actually run the code as well. Let's fix it. Okay, now it should. So that's if statements. One other thing we can have is for loops. I'm not going to go too much into those. So you can say, for example, for I in range 5, meaning range means count from 0 to 5. And within the for loop, notice the indented block. Do whatever's in the indented block. So it will print I for every turn of the loop. So in this case, I starts from 0, print 0. We say the end of the print. Normally, if you don't put an end switch to the print, it assumes the end is a new line, so it will write them one by one. What we're doing here is we're saying, okay, once you print, don't go to a new line, instead put a space, right? It's easier to see, for example, if I put something like that here, you'll see that it puts those there. If you put a space, it puts spaces, and not having this, or this being default, is basically the same as saying put a new line here, which would be what we see normally, right? So here I'm just going to put space, so you get 1, 2, 3, 4, and if, let's say if I make this into 15, it will count until 14, 0 to 14, so 15 things. And you can actually put other things here, so it can do multiple things within the for. And for I can actually be a range, or it can take any array that you have in your program. So for example, you can say, remember these grades here, or fruits, for example. You can say for I in fruits from before, and it will actually say apple, banana, cherry, and so on and so forth, right? Remember, it was apple, banana, and cherry. So essentially, for goes through any number of any number of items in a list, either created right there with range or pre-existing, and it will work. So actually, let's add that as well. Okay, so here's the example for that one. Right? So it might be fruits like apple, banana, and cherry. One other thing you might need with any programming language is obviously functions. So you want to define functions beforehand and then hopefully use those functions later on. So here's an example of that. Let me bring this over so that I don't have to type. Right. Actually, I'm going to close these so that we don't need to waste the space. So, for example, I can create a function with the keyword def. I'll say def, and the name of my function is calculate average, and it takes within the function a list of numbers. And after the function, I can write this string here that will become the documentation of calculate average. So when I run this code, if I come over calculate average later on, over here, for example, in another cell, calculate average, and if I go over this, it will give me some documentation on the function. It says it takes a numbers, which is a list of any, and gives back a floating point number. And it says it will return the average of a list of numbers. Where does it know this from? Because we wrote it here. That's how it generates documentation. Okay, so what it does is, for example, it takes the numbers. There's a nice function in Python that's built in called sum, which will just give you the sum of any list, right? Sorry. For example, obviously the sum of these is 61. And then count, remember we said len counts any array, so it basically returns total and count. So now we have a nice packaged function that will calculate the average of any number of numbers. So again, taking our grades array and the average variable, we can equate to calculate average grades and then print that, right? So notice it says it takes these and it prints out average grade because this is remember the f string, it plugs in the average variable we calculated before using the calculate average function and formats it. What this does is it says format it as a floating point number with 1 decimal digit after the point. So if I say, for example, here 3 decimal digits after the point, you'll get something like this. Or if I say don't do anything after the point, it'll just round to the closest integer, right? So that's useful for formatting. Now, one other thing is kind of default values. So for example, let's say you write a function called greet, which will take a name and it will say some greeting, comma, name, right? So if you, for example, if I say greet Bob with the greeting good morning, it will say good morning, Bob. But if I don't give the greeting, if I just call the function with a single string, in this case the name, it will default to hello. So when I run this, the first one I didn't give a second greeting thing. It basically says hello Alice. But if I also give the greeting for that function that I created, it says good morning Bob, uses that greeting. So you can have kind of essentially functions that are adaptable, right? So we'll have a simple version, and a more complicated version. Another example might be something like, let's say I write power of x and y I'll keep to 2 for now. And what we'll do is it will return x to the power y, right? And if I don't say anything, if I say power of just 3 to the power of 2 is going to be 8. It will, oh, sorry, 3 to the power of 2, obviously. 3 squared is going to be 9, so it gives out 9. But if I say 3 to the power 3, so the cube of 3 would be 27, right? Or the cube of 2 would be 8. But if I don't give that, the square of it will default to the square of 2. So you can actually write a documentation here. Give the y power of x defaults to x squared if y is not given, right? So now I have that, and later on if I use this function somewhere else, if I say power of, and if I look at the documentation, it says gives the y power of x defaults to x squared if y is not given. So you can document your own function. Yeah. So the next thing we want to do is text importing libraries, right? So usually the things we're going to import are going to be basic libraries that we're going to use for the whole course, and it just makes sense to import them in every case, even if you're not going to use them. And they have certain known kind of conventional short aliases that we use. So NumPy, like I said, is numerical arrays and math, and usually it's shortened NP. So anywhere when code, when you say NP dot something, people know you're referring to some function out of NumPy. Pandas is, like I said, the data frames, tables, and data wrangling library, and it's usually shortened as PD. For Matplotlib, we usually just use the pyplot sub-library, and that's usually shortened to PLT. And SciPy, if you're using, for example, statistics from SciPy, you import stats. From SciPy, you can also import, for example, you can integrate, import, for example, OD int. So SciPy has a bunch of different sub things. So, for example, SciPy has stats, it has integrate. For bioinformatics, we're going to use kind of intro, we're going to use a lot of the stats. For systems biology, we're going to use some amount of integrate. And you can see the sub packages here, right? It has basically all of science here. There's clustering libraries, constants, Fourier transforms, integrate, so integration routines for ordinary differential equations. You have optimization functions, you have statistics, spatial data structures, signal processing, etc. You basically bring in what you need, right? So for this kind of introduction, we're just going to need stat. So we'll import all of these, and let's start with, and you can actually check whether these are important and what versions you have, right? So for example, NumPy, like I said, NP is, we basically said import NumPy. We could have just said import NumPy, but then every time we use some function out of NumPy, would have to write NumPy dot something. However, since we're going to use it very often, we just shorten it to MP, and PD, and PLT, and so on and so forth. So NP version, Pandas version, and PLT version. And these are obviously the versions available on Colab. If you kind of have a local installation of Jupyter and Python, your versions might be different. Later on, when you're watching this video, if Colab has upgraded their versions, that might be different. But right now, as of February 2026, these are the versions on Colab. So let's start with a quick introduction to NumPy. We'll just say bring in these. Just a quick introduction text here. So NumPy basically comes with its own array, something called an ND array. Usually you don't have to, it's a kind of like a Python list, but it's written in C and is very fast for numerical data. Notice that, for example, Python lists can hold everything. They can hold names of fruits, or they can hold integers, etc. Python arrays, NumPy arrays are made to basically hold numbers and to be very fast with doing stuff with numbers. They can hold strings as well, but they're not optimized for it. So usually when we use ND arrays, or when NumPy uses ND arrays, because it's usually very transparent, you can give it a Python array list and it will on the fly change that into an ND array anyway. So let's start with creating arrays. Right? So let me just add that here as well. So you can build them directly from lists, or you can build them kind of, let me get that code so we can go over it. Again, I'm importing NumPy again. Actually, I don't need to, because I did over here in this cell. One thing this will help to kind of illustrate, though, is when using kind of Jupyter Notebooks, one thing you have to be careful about is whatever you defined before, whatever cells you ran before, they go into the system in the order that you run them, right? So if somehow this cell moves to where someplace before, Python is imported, NumPy is, for example, imported. Where was that imported? Oh, sorry. Let's move this back. And let's say we take this and move it down all the way. So I import this, and then I run the cell before, and the cell before will work just fine. The problem is if you, for example, restart the session, right? So that basically removes everything we did, and then we run all of these again up to, where was our Python thing? Okay, so run everything. How do we do that? Over here? No. Run all. Huh. Okay, I guess you could do it with manually. Normally there should be a button that says run everything above it, but I can't find it right now. Anyway, well, the quick and easy way to run everything is you can just go Shift Enter. Shift Enter is like Command Enter. Remember, Command Enter runs the cell. Shift Enter will run the cell and move to the next cell. So if you just press Shift Enter all the time, you will just run the whole thing from the beginning. Okay. You see what happened here? We got an error saying NumPy is not defined. Well, this used to work because the import was above where we first used NumPy. So when I was writing the thing, if I import it here from a later cell and use it here, it will work fine. But next time I run the thing, if I haven't imported the thing before, you'll get an error. So what this has to happen is this has to be before the first time I use NumPy. Now I import everything, and now this one is happy. So one quick thing to do is, if you're using this for a homework or something, just realize that you might, while creating the notebook, do things out of order. So just make sure once you've created the notebook that everything works in order. So the way you do that is you restart the session. Yes. And then you can actually say, just to make double sure, you can say clear all outputs. So all the outputs are now gone. And then you can say run all, right? So, and make sure that there are no errors in the cells. So if everything is in the right order and everything comes after what they're supposed to come after, then you won't get any errors. Otherwise, if you did something out of order while development, you might get an error. So I don't actually want the new lines here. These are just for kind of nicer looks, but yeah, actually let's keep them. Okay, so how do we use NumPy? Creating arrays. So you can create an array directly from a Python list. You give the list 1, 2, 3, 4, 5, and you say np. Remember, np is short for NumPy, np.array. Now a is now, notice that it is an nd array. When I move my mouse there, it goes away, but it shows you that that variable a is now an nd array. And it's a one-dimensional array. And you can ask for its shape and its d-type. And if I do that, if the shape, it tells me it's 5 in one dimension, and that's the only dimension, so single dimension, and it's made up of 64-bit integers. You can create matrices out of lists of lists. Again, if you make that and run it, you see that you get the 2D array. Now the shape is 3 by 3, so 3 columns, 3 rows. You can also create things out of you can create, for example, an array of zeros, right? So that's a 3 by 4 matrix filled with all zeros. You can have a matrix made up of ones, so a 2 by 3 matrix filled with ones. You can use what's called a range, right? Essentially, it creates a range array for you. So for example, you say start from 0 up to 10, not including 10, go 2 by 2. So it says 0, 2, 4, 6, and 8. And how do you know this is what's supposed to be? So how do you know this is the first thing is the start, the second is what you go up to, and the third thing is by what amount? If you go in, it tells you that a range, the first thing you enter is start, the second thing you enter is stop, and the last thing you enter is step. So it will actually give you the documentation if you float over it. Linspace is kind of different. It basically says take the distance between 0 and 1 and divide it into 5 pieces, right? So for example, between 0 and 1, if I divide by 5 pieces, I get 0 to 0.25, 0.25 to half, and so on and so forth. If I actually change this into, say, 10, you'll see that it actually divides it to 10 equal pieces. Actually, 10 equal pieces here doesn't work, but if I divide by to 11 pieces, then I'll get kind of nice numbers. Because obviously it has to be an odd number to divide it evenly. You can have random numbers, so you can say, give me a 3x3 matrix made up of random numbers, and it will be as follows. And every time you run this, notice that it will be different random numbers, right? Okay, so that's how you create stuff. One other thing you do with NumPy is you can have vectorized operations. And what does that mean? So basically NumPy can treat the whole kind of entire array as a single number. So just like we say, for example, 5 times 6 in Python, you get 30. But if I say in Python, if I say 1, 2, 3, 4, 5 times 6, what Python does is it basically repeats the thing 6 times. But mathematically speaking, what I would want is kind of multiply 1 with 6, 2 with 6, 3 with 6, 4 with 6, and 5 with 6. That's what NumPy does. So if I say make an NP array out of this and multiply with 6, notice that it treated this whole thing like a number, right? But it element-wise multiplies everything with 6. So here are some other examples. For example, to be able to do this in Python, what you would have to do is write kind of a give back the array such that everything is multiplied with 6. You'd have to write a for loop. You would say for I in range, let's say this is my for I in this thing, then, right? And I would basically have some new array, or let's call it new list, and that would have for I in that new list append, remember append, I times 6, and then finally give me back new list. And that would actually do the same thing, but I would have to use this for loop, which is using loops in Python directly is typically slower. So what NumPy gives you is essentially a way to not have for loops and do this type of thing directly with one command. Plus it works, kind of NumPy uses C underneath, so it's much faster than doing it with Python. So what I'm going to do is copy that. So this is actually called what we call vectorized math. So you don't have to use loops. So we'll create our NumPy array from 1 to 5, very simple array. Call it A. So the original is A. For example, you can say A times 2, basically say, just like we did with the 6 a minute ago, A times 2 will give you a new NP array with every element of A multiplied by 2. Or A double asterisk 2 means take the power of 2, so it will take every element of A and take the square of it. Sum will add up everything in A, give you a number. Mean will give you the average, standard deviation will give you the standard deviation, etc. And you can actually do the same thing with, actually let's go step by step. So that's vectorized numbers over here. So we already talked about it. We don't need this. Right, so you take the original array and you can just say A times 2, A times... Now obviously this print is just to show you what happens here. You can just basically use this directly, right? Take the 4th power of everything in A and you'll get the array, and then you can use it, basically you can chain things as well. Take the 4th power and everything in A and add 5, right? So now that becomes this. And then ask the question, is the resulting number let's say greater than 450, right? And if I run that, I get a new array saying, okay, for the first two, taking the fourth power and adding 5 is not greater than 50. The others, it is greater than 50, and so forth. So one other thing we can do is essentially with matrices, you can index by row and column. You can't do that directly in Python lists, but NP arrays, so if you give it a list of lists and make a matrix out of it, you can say, give me the first row, second column, first row, but first again being actually second, because this is, remember, this is row number 0. This is row number 1, and this is row number 2. And same thing for the columns. So when you say, give me matrix 1, 2, what you're basically saying is give me the second row and the third column, right? Because it's 0 index, so you get 6. First row would be row 0, so if you just give it a single thing, it will give you an NP array of the first row of one-dimensional thing. If you say, put a colon for the first thing, and then say, give me -1, give me the last column. So 3, 6, 9, that's what it does. And you can do slices, right? So give me the first 3 rows. So give me row 0, 1, 2, and columns only 1 to 3, not including 3. So this should basically give you the whole matrix, right? So actually, let's run it and see. Submatrix, it gives you 2, 3. Okay, what did it do? Oh, it starts from 1. So this is column 1. So it gives you 5, 6. And it starts from 0, row 0 up to 2. So it doesn't include row 2. And it starts from 1. So it doesn't include kind of column 1. It doesn't include the last row, so it gives you 2, 3, 5, 6. Okay. And finally, like I said, you can actually make a mask. We did that just a minute ago. For example, take an array and say, give me everything that's greater than 20. So this will return false, 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 true, false, true, false, true, right? Because they will be 10 will be less than 20. Actually, let's kind of look at the mask here to make so that you can see. Yeah, so the first one is false because A at the first thing is less than 20, so greater than 20 is false. A at the second position is greater than 20, so that's true, and so on and so forth. So you get this mask array, and you can actually give that mask array to the original array, saying, give me everything in A where this is actually true, right? And you should be able to do that same thing with the matrix as well. So in the matrix, let's say the mask is matrix less than 5, right? So let's look at the mask. It's noticed that these 2 are less than 5, these 3 are less than 5, that's less than 5, and the rest is more than 5. And I don't know if now we can use this to mask the matrix. It probably won't work because it will ask for 2 numbers. But it actually did work, except it's giving us, oh yeah, so it flattens out the matrix so that, sorry, let's fix this so we don't get problems later on. Right. basically took this row and the beginning of that row and flattened it out into a single array. So it still works. Okay. So that's NumPy. Let's do kind of a practical analysis example. Let's say we want to use NumPy. Oh, sorry. This is not a code. This, if you get kind of syntax errors and cells you don't expect, it might be because it is supposed to be a text cell, but you made a code cell. So let's convert this into a code cell. How do we do that? I'm not gonna. Just gonna delete it and create a new text cell and paste. Okay. Practical example, exam score analysis. So let's generate some realistic student data and complete a full summary without ever using a loop, right? So let's go over this. One thing I want to show you though is, remember this, for a minute, let's go back here. Notice that anytime I run this, these are kind of constantly new random numbers. If you want them to be random but not change with every run, you can set the seed on the random algorithm, right? So np random seed, and if you say, let's say 1, 2, 3, 4, just to give it some seed number, what will happen is you'll still get these random numbers, but every time you run it, it will be the same random numbers. So it will be random but reproducible. So the reason I explain, kind of talk about that is over here, we'll actually use that. So let me get that code from here. Okay, so we don't need to import NumPy. So we'll set the seed to 42 in the beginning, and we'll generate scores. And for that, we'll use np random, so NumPy random, and we'll use the normal distribution. So it will generate a bunch of scores that are normally distributed, just like a normal curve. And notice we give log 72. Log for normal is the mean of the normal distribution. So our curve will be 72. And the scale is the standard deviation. And so people's scores will vary by 12 or so. And we want 30 students. Again, you can go into normal and it will give you what each one of these things is. And you can get documentation for this normally by Shift Tab. But it doesn't seem to, it has this, but it doesn't have full documentation. But we can always go and say, you can do several things for any function you want to learn about. You can go to Google and ask for whatever you're looking for, and it will basically tell you, kind of give you everything for the function you're looking for. So for example, NumPy random normal, if you don't give anything, it creates a normal distribution at 0.0 with standard deviation 1, so the standard normal. And size none means if size is none, a single value is returned. So you can actually try that on a separate cell if you want to make sure it works how you think it works. This is the nice thing about kind of notebooks, is that, for example, if I just run this without anything, I expect it to have a random variable at 0, standard deviation of 1, so it should be around 0, but it will vary a bit, and it will create just one number. So if I run this, yeah, I get numbers around 0, randomly distributed, and so on and so forth. So if I say location 72 and scale 12, I should get numbers every time some kind of centered around 72, but plus or minus 12, so to speak, right? So I'll get different scores, kind of like grades from an exam. And finally, if I say size 30, it will basically create 30 of these, right? Which is exactly what we want. And I'm going to kind of give you a bit of a spoiler here, but I can actually take this and draw a histogram of them, and they should be roughly a normal distribution. So if I actually increase this to 300, it looks more like a normal. Let's make it really large. Yeah, it's a normal distribution centered around, so it's a bell curve centered around, if there's 3,000 of these, it will be a bell curve centered around 72. Let's make it even bigger. See how well Colab, now it's almost a perfect normal. And you can actually change the number of bins. Let me see. Array like, well, how do we change the number of bins here? Bins, oh, there we go. Let's say I want not just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins, but let's say I want 50 bins. So it looks more kind of like a thing. And let's make it even better. 500 bins. Why not? Very nice normal distribution. So basically, kind of jumped ahead a bit, but what we're doing is we're generating 30 students, and kind of this will be their grade distribution, right? And every time I run it, it will be slightly different. But if I kind of set the seed to the same thing every time, it will be random, but it will be predictable random. So with this seed, it will always be exactly the same thing. If I change the seed a bit, it will be a different thing, but it will always be the same thing. Okay, so let's see what this does. So we create the scores of the students. We do clip, which is if there are any students who kind of very randomly got scores above 100 or less than 0, because the normal distribution can presumably have very low kind of probability, but a very low probability can have negative numbers or 100 in this case, even though it's centered at 72. We throw those out, and then we say scores, class size is going to be typically 30, but if we throw out any numbers, it will be less. Give me the average, the median, the standard deviation, the highest, lowest, and how many of those passed. So how many people passed, basically scores that are greater than or equal to 60, and the sum of those, right? So you'll have 24 students that are passed, class size, and so on and so forth. So that's how you use NumPy. Okay. Now, from there, let's take a look at the second library in our set of libraries, and that's going to be Pandas. So let's put that there. Make that into a nice little heading. So yeah, we've done Python fundamentals. We've done, okay, so something is not exactly right here. Should be second order. Okay. See now. Getting started with Python is first order. Python fundamentals is second level. This is third level, so this should be below that, but why isn't it? I don't know. Okay, let's close these up to make sure everything is like we thought it would be. Yeah, okay, so I guess the table of contents is buggy. Anyway, so what Pandas gives you is what are called data frames, which are kind of tables of mixed values. So this is going to be especially useful when you're kind of taking data of multiple modalities, like patient data, with each patient's, say, medical information, like text-based medical information, plus numbers like temperatures, blood pressures, amounts of glucose, etc., lab results. When they all live in the same table, Pandas allows you to kind of manipulate those tables kind of easily. And you can think of it, like I said before, as an Excel spreadsheet that you can control with code. So let's kind of start with a very simple example. Let's say we have a mixture table. Again, you don't need to import pandas here, but I'm just doing it for safety because we already imported it back here somewhere. Where did we import it? Oh, importing libraries, there you are. Okay, so we already imported it here, but I'm gonna just import it. Doesn't, again, it's no problem if you have to import it again, just not necessary. So let's say my data, which is a data frame, is basically a list of names: Alice, Bob, Charlie, Diana, Eve, their ages, so they're assumed to be on the same order, their majors, so which department they are in, physics, computer science, biology, etc., and their GPAs. When I give this dictionary to data frame, pd.dataframe, it gives me back a data frame, and then I can look at the shape of the data frame and then which columns it has and so on and so forth. So this is going to be the data frame. So nice little table with everything here in this data arranged as I'd expect. The shape is 5 rows by 4 columns, and the column names are name, age, major, and GPA. And in Colab, you can actually also now, I think, see this somewhere. Yeah, DF. So it gives you a nice kind of a summary of whatever data frames are in your notebook at that given moment. Right. So, okay, we imported pandas. We have this data frame. Now, what can we do with it? So we have some very quick kind of functions that are generally useful. Probably the most useful one is head. So generally on data frames, when you load them from the outside, either import through CSVs, etc., they will be huge. So you won't be able to kind of print out the whole thing in screen. But what you want to do is maybe see the first few columns of it or first few rows of it. Head allows you to do that. So for example, head 3 of data frame will give you just the first 3 rows of the data. Describe will give you summary statistics for any given numeric columns, and info will give you kind of a generalized information about the data frame. This is useful for kind of daily exploration. So for our example, our data frame, when I say head, as expected, head 3 just gives me the first 3 things, the first 3 rows. Let's see what describe does. The only 2 numerical columns in the data frame are age and GPA. It tells me both have 5 values, and you can have missing values if you want, or if it's necessary. It tells me that the average age is 25.8, the average GPA is 3.62. From these columns, the standard deviations, minimums, maximums, 25th percentile, 75th percentile, and the median. And info basically tells me that this is a data frame. It has kind of 5 entries, meaning 5 rows, and it has 4 data columns, and that each column has a different data type. So name is an object, which is another way of saying string, and then age is an integer, GPA is a floating point, meaning decimal number, and it's basically this thing is using 292 bytes in memory, which is again important when you think about kind of what large things you can bring in. So how do we bring in something kind of new from the outside? For Colab, actually, you can connect the notebook directly to your Google Drive and use Google Drive to bring in stuff. And I'll show you based on that. Okay, so let me go to my kind of Google Drive. Again, if you have a paid account, this will have more kind of storage, but even with a free Google account, I think you have, I don't know, 25 gigabytes or 5 gigabytes, something like that. Anyway, in your drive, you will have a directory called Colab Notebooks, and whatever you created in Colab will actually be there. So for example, my first notebook that we're creating right now is actually here, and I can go ahead and download it to use someplace else, like locally, or once you're finished with it, for example, you might send it in as a homework assignment and so on and so forth. Let me create a new folder here called data. And within data, I'm going to put in a CSV file. So I'll just drag and drop. It'll start uploading. Okay, injuries, statistics, work-related claims, 2018. So if I actually look at this with Google Numbers, it's basically a bunch of okay, why is it all total? Okay, so it's basically different groups and things. Anyway, we'll figure it out. Right, now what I can do is, let's close this. Let's actually give it a easier name. Rename injuries 2018. Okay, so this is one CSV file. It doesn't really matter what the kind of content of the file is. It's just a rather big CSV file, so about 354 kilobytes. And what I'm going to do is I'm going to put this into my data under Colab Notebooks and my Google Drive, and I can use essentially Google to bring that in, Colab to bring it in. So what you do is you load Google Drive as a library. So from I think google.colab, yeah, import drive. So you import that, and you say drive.mount content drive, and that will mount your drive under kind of the content directory. So let's run this. Now you should get kind of a permission dialog on your Google account saying, do you allow this notebook to access your Google Drive files? And yeah, you say yes, since it's your own notebook, it's no problem. I don't have my security key, other ways to verify. Yeah, let me just get that from there, Google, right, and we need that. Okay, it will ask for a bunch of authorizations. Yeah, and then it should succeed. Yeah, now it's mounted at content.drive. As a matter of fact, if you kind of go into this and let's see, where do we get the terminal? Oh, there we are. If you open up a terminal, you'll see there's drive, there's sample data, and under drive is my whole drive. So under that, there's going to be Colab. See what there is. Oh, there's my drive. And under that, there's going to be Colab Notebooks. And here there is my stuff. And under that, there's a data directory that we just made. And under that, there's injuries.csv. So you can just copy all of this stuff, right? And say, now I can actually load this file from within Python. So I'll say from Pandas, read CSV. So that's a comma delimited file. Remember, this thing is basically, if you open it up as text, open with text editor. I don't know if the online text editor can open it, but yeah, authorized text. Again. Yes, continue. Right. It's basically a text file with number, comma, whatever, comma, and so on and so forth. Okay, so what it does will be read that, and what it wants me to give me the file path. The file path in this case is that injuries 2018.csv. And let's call these the injuries data frame, right? And if I run this, we get an error saying, okay, it didn't like one of the things. Decode byte in position 5. I guess this file has some illegal values. So let me just pause this recording and find the better file here. Okay, so instead I got this kind of products 10,000 file, which is, when you look at it, it's basically, let me bring you another text editor from above. It's basically a bunch of products, right? So each one has an index, the name of the product, the description, brand, what category it's in, price, what currency the price is, the stock, meaning how many they have of the product, the store, the color, and so on and so forth. So it's a big file with 10,000 lines. That's why it's called product 10,000. So if we go back here, now we can just say pandas read CSV from our drive, this products, whatever, products 10,000. And now I can use the things from before, right? I can say, okay, sorry, we actually called this injuries df. Let's call this products df so that it's not confusing. And I can say now use all of this stuff from before. So I can say products df info. Let's see what it is. So it has 12 kind of columns. It found out the data types for the columns. The objects are string type, etc. It's using more than a megabyte of space. You can actually look at describe. So, for example, it shows us automatically that, well, EAN and internal ID is not that interesting, but we know that on average we have about 500 of every product. Most we have is 1,000. The least we have is 1. On average, the price of a product is about $500. Obviously, this is kind of a synthetic data set, so it's very nice and tidy, but it works. Okay, so that's how you would kind of read data, and more importantly, you use this pattern to kind of mount your drive to some place that the notebook can use it. Right. So how do we select and filter data? Again, I'm not going to use this kind of big table. I'm going to use our own thing so that it's kind of more obvious how to do filtering and so selecting and filtering. So we'll use this toy example again. So again, we have these students with their ages and the majors and so on and so forth. You can print individual columns, right? So if I just say the name of the data frame, so df, and then square brackets the column, it will just give me this column, the names. If I give two things, it will give me a data frame made out of those multiple columns, so I can kind of vertically slice my data set. I can filter rows by condition, saying give me only the CF students, meaning from the data frame, so this is the outer part, find every place where the data frame major is equal to CS and only give me those. You can find, for example, again, say find the locations where the GPA is, the rows where the GPA is greater than 3.5 and the age is less than 28, and essentially give me those rows from the DF, and you can sort them, right? So it all works. Again, you can also, like I said, select by columns, or you can select by rows and columns by kind of using the colon thing. So for an existing frame, can you add, you can also add columns directly, right? So if you have a frame that already exists, like our kind of existing DF here. So let me take that DF, right? And let me add a new column called status to these students, right? So before, let's print the DF, and let's say this is before. And give it a few new lines on both sides so that it's obvious. And now also do an after. And what I'm going to do is I'm going to add a new column to the DF, and notice that the DF doesn't right now have a status column, right? It only has name, age, major, and GPA. And so if I access a column that doesn't exist, I can basically add a new list here, then that will become that column. And what I will do is I will say let's say, for example, I can say status okay to everybody, right? And then print the df. Let's actually create the df from scratch for this cell so that we can play with it. So I have the original thing. So before we have this, later we have a new column called with all status. Okay, so what if I want this status to be though kind of different for everybody depending on how they are, right? So let's say if the GPA is above 3.7, above or equal to 3.7, it's an honor student, otherwise it's a kind of regular student, right? You can use a function called, a kind of thing called apply. So you can say GPA, so you can have computed variables. You can say apply, and you give it an anonymous function, so some function of x where it's honors if x is greater than or equal to 3.7, else make it a regular student. So this function doesn't have to be like this. I'll show you an example later on. So when you run this, notice that everybody that has a GPA of 3.8 becomes an honor student. So the new column can get calculated by the existing column. So what I did with this lambda here is what's called an anonymous function. You can just as well do something like this. You can say here def student status given their GPA, and if GPA is greater than or equal to 3.7, then return honors, else it's misspelled, but I'm going to leave it like that so that we can see the change here. Return regular. So it's just a function, right? So I can just say here student status and run it, and it will work just fine. It's the same thing, right? So I define a function and basically say apply this function to all of the GPAs, and the results put it into the status function. Instead of writing this whole function as a separate thing, let me comment this out. Instead, I just put lambda x if x, whatever is given, is greater than or equal to 3.7, then return honors student, else return regular. So this is just shorthand for writing this function, and it's kind of like Python syntax candy. You don't need it, but if you know how to use it, it makes kind of for less typing. All right. By the way, one thing that I'm going to kind of go into, for example, things like this. How do you import, kind of mount a Google Drive to a Colab notebook, etc. And for things like, for example, what does this mean, right? If you see something that you don't understand in a piece of code, you can actually use Gemini or whatever model you like for that. So you can, for example, if you don't understand this, you can say, what does this do? And shift enter and then say that. And it will spend a bit of time. If you have a kind of pegged account, I think it's faster, but it gives you a nice explanation of what this does. Or you can say, how do I mount my Google Drive to a Colab notebook? And it should give you the same kind of trick. Oh, it's actually directly puts it in here. See what we wrote? It will just, you can just say accept. It just plugged it in the notebook directly. So just keep that in mind. Right. So last thing I want to talk about is where's the rest of my code? Just a minute. Oh, last thing I want to talk about is group by. So group by is essentially a way of aggregating things in a data frame, right? So you can say, for example, group all of the students by their majors. So combine all, kind of group all of the CS students together, all the biology students together, and for each group, do some aggregations. Find the average GPA of the group, find the number of people in the group, and find the average age in the group. And let's say round everything up by 2. So you will get something like this. So there's one biology student, their age is 22, they have an average, they have a GPA of 3.9, but there are 3 CS students, the average GPA is 3.35 and 29. So that's essentially Pandas, right? What it helps you do is you can load in huge amounts of data. You can extract and kind of slice and dice that tabular data with Pandas. You can get an exploratory view of it. You can calculate new columns based on old columns. So, like, again, I'm going to come back to the same definition. It's basically Excel that you can program in Python, right? Right. So, the last couple of things we're going to look at. One of it is visualization, which is what we do with Matplotlib. So essentially, we're gonna talk about how to do figures in Matplotlib. Right. Okay. So usually the pattern in Matplotlib is always the same. You create a figure, then plot your data. Sorry. And then add any labels, title, grid, and then finally show the plot. If you don't have the figure and the show, you just kind of can create ad hoc one-off visualizations like we did in the beginning of this video. But usually it's better to kind of put them into plots. So let's start with very simple ones. I'm gonna spend too much time here. Again, when you want a certain kind of plot, you can ask Gemini or ChatGPT, and they give you very nice code. And if you don't like it, you can say change this, and they'll change it, and so on and so forth. Let's start though with a line plot, right? The simplest type. So you would do something like this. Again, you don't need to import these because we did in the beginning, but just to make sure. Remember linspace, so I'm creating a bunch of x's between 0 and 1, 100 of them, equidistant from each other. And y is going to be the sign of those x's. Remember, NumPy does vectorized operations. So if I don't do the rest, let me just run this. And here, let's just take a look at x. X is basically numbers from 0 to 10 with equal separation between them, 100 of them, and y are just the sign value, kind of sign applied to each one of those x's, right? So what we're going to do here is we're going to create the figure. It's going to be 8 by 4, meaning it's going to be long and kind of wider, twice as wide as it's long. Usually this is in inches for print, but you can change the unit in figure. We'll say plot x against y with, let's say, steel blue color with a line width of 2, and give the plot a title of sine wave. the x-axis label will be x, the y-axis label will be sine of x, and also have a grid which is 30% transparent or 30% visible, meaning 70% transparent. So if you run this, you get this nice plot, right? See the sine wave, the kind of less transparent thing. So for example, if I make this 0.9, it should get much darker and so on. So there's huge amounts of things you can play with this with here. You can change the color to red and so on and so forth. So there's incredible amounts of things you can actually, for example, put an AB line, I think, what was it called? Line? Anyway, I don't kind of tend to memorize all of the things you can do whenever you want to do something with Matplotlib. Let's say you want a little box here saying something. You can just again ask Gemini or ChatGPT or look at the documentation on Google. But it is possible. One thing that's kind of done a lot, which kind of serves you well to know, what is this? Yeah, we don't need this anymore, is how to draw several things on the same plot. So you can call plot PLT plot multiple times on the same figure. You'll get several of the same kind of different things. So an example would be, what if I wanted to plot both sine and cosine of the same thing, right? Same thing, I create x, and then I plot the sine of it and the cosine of it with different, the cosine will have different styles. Obviously, I'll change the plot title, etc. But it works very nice, right? So if I don't give the colors here, remember I gave the color, it will just use some color in a certain order, but also line style allows me to do stuff like this. For example, I can add plot legend to give it cosine of x and so on and so forth. So that's that. We already talked about bar charts and histograms. Well, actually, we did a histogram on the fly a minute ago, but that's another type of thing you can plot with Matplotlib. Take a look at this. So, for example, let's say I have, again, the majors, physics, CS, biology, and math. Let's say I have 15 students in physics, 25 in CS, 12 in biology, and 18 in math. I can actually draw, let me do this and comment that out. You just create a figure again with a certain size. You say, make a bar plot of the majors versus the counts. You can actually give it hexadecimal colors, RGB colors for individual things you want. And you can say, again, give the plot title, plot label. Here you also kind of you can put text of the majors on each one of the bars. So sorry, the actual counts on each one of the bars. This is kind of getting fancy. Just to show you what it does. If you get rid of this, you no longer have those things. This is kind of a manual thing you can do just to show you that it is possible. So that's a bar graph, and the histogram, like I said, we already saw that before, but let's just run it again as part of a plot. So you can have something like this, but now it also has, oh, it's called an AXV line. I thought it was called an AB line before. So you can put kind of a line at a certain position showing something you want using AXV line. So that's that. One thing that's we're gonna kind of used very often in a lot of science, but in bioinformatics, is scatter plots, which are plots that kind of essentially an XY plot, but with points they can be colored in different ways. Here's kind of an example. Again, we'll put random plots, but I'll set the seed. So let's say the hour studied by a human, by a student, is some random uniform number between 1 and 10 hours, let's say per week. And the exam score of that student can be calculated by a baseline of 40 times 5 times the hours studied, plus some random noise, right? Plus or minus 5 points based on kind of random effects. So we're doing this for 50 students, and we'll scatter the hours studied versus the exam score for the student, and we'll color the points by exam score, so they will be kind of different colors as the exam score gets higher. And we will also kind of have the points will be kind of transparent, so we don't see the overlaps. And we'll also put a color score bar, so we see kind of like a heat map what the score was, right? So a bunch of little niceties. So you get something like this, right? This many hours studied, you get this many scores, and so on and so forth. A lot of this obviously is not necessary. You can just quickly do something like this, right? You don't need that. You don't need a color bar. And you would still get a decent thing, but this makes it kind of nicer. You don't even need any of these, right? You can just have some naked plot. Obviously, putting all of that makes it nicer. And again, some of this stuff you get used to and you remember the names of the functions directly, especially if you do it very often. I tend to learn these very well while I'm writing a paper, and then I forget them and then I relearn them. But these days, again, just you can ask the AI to say, okay, something like, if you pick all of this stuff, I want the colors of the scatter plot to be from green to red. Let's see what it does. Okay, see, it basically changed the color map from that to that, and I say accept, and thank you, go away, and I run it. Not bad, right? The other one was prettier. Okay. So that's that. One last thing that's useful is having subplots. So essentially having 2 or 3 plots right next to each other, sometimes sharing an axis. I'll again give a very kind of a involved example. Let's say I have 3 panels. So it's 1 column and 3 rows. So they're kind of all one under the other. So they're organized as a single column, but 3 things, one below the other. So the first thing is a line plot. Second thing is a bar chart. Third thing is a histogram. So if I do that, this is 1 row and 3 columns. So 3 of them right next to each other. And essentially you can get them all together. If you kind of change the thing to the other way, and obviously it has to be longer than it is, taller than it is wide, get the same thing kind of like this, right? So, and the good thing about this is, for example, if they have the same x-axis, if you put them together, they will be kind of in sync. They will share the same, not share, but they will be aligned along the same axis. So let's change this back. Ooh. Right. Okay, finally, we'll talk a bit about SciPy and then end this video, which has gotten very long. So essentially that's SciPy is for scientific computing. And what I'm going to do is kind of show you one example where we'll use SciPy. For example, for curve fitting, that's very kind of typical usage of somewhere you would use SciPy. So SciPy stats has the statistics functions. Usually NumPy is enough for most statistics, but if you want to go further, it has things like skewness, kurtosis, etc. But what SciPy, it's the strong part of SciPy is not necessarily its stats. There's actually other libraries like stats models that are kind of more powerful there. SciPy is actually a very good overall library for things like numerical optimization and things like curve fitting, etc. So we'll do one example on curve fitting, just to show you how this might work. So let me get the code again. So here in SciPy, we don't get the whole library, we get what we need. So from SciPy optimize, we will get curve fit. We already have these, we've imported them, so we don't need them. The rest we do need. And you can kind of look at this from the documentation or ask Gemini or some AI. Optimize curve fit, and you can see the manual here. Basically, it says you give it the function you want to fit, the x data and y data, and some other kind of settings if you want, and it basically give you back the kind of the parameters for the function. So here's the example. Let's say we want to fit a line. So the simplest thing you want to fit is kind of a linear model. It has x, y is equal to x times the slope plus the intercept. So the first thing is always the independent variable, and the next two things are the parameters. So let's say I create some data here. Let's for now not do the curve fit, and we will just look at the data, right, with the scatter plot, and like this. So let's just run this. So this is our studied versus exam score from before. Now we want to find the best line fit for this, and we can use curve fit. So we define the model, and here for the fit for SciPy, what we say is, okay, take the linear model, try to fit to hours and scores, and give me the parameters you find. And the parameters are going to be the same number in same order as whatever comes after x in the function I give it, which was linear model. And therefore, it's going to be slope and intercept. It will give me slope and intercept. And finally, we will later plot it. So it says the best thing it found was 4.88 slope times hours plus 40 will give you kind of the thing. And we did that, right? So 40 baseline, so it found the intercept rather correctly. 5 times hours, 4.88 is close enough to 5 because there's noise. That's the best it can do, and so on and so forth. And then we can take that function and add it to our plot and say this is the linear regression of this function, and it works just fine. Let's say I wanted to fit not a linear model, but let's say I wanted to fit quadratic model to this. So obviously it's going to have, let's call them A, B, and C, and it's going to be A times x to the power 2 plus B times x plus C, right? So we're gonna this time use the quadratic model, and the parameters are gonna get back are gonna be A, B, and C. So best fit is A, B, and C. Okay, for now let's not plot it. Let's see what it does first and run this. So you get almost 0 for the kind of the square, and then the slope and the intercept more or less remain the same. So if we actually did plot this here, we have to change how we fit it. Obviously, we're gonna have A, B, and C here. And the fit, label fit, is going to be, again, let's copy this from here to there so that that's printed on the plot as well, and run. Ooh, I don't like something. Oh, we need to change the name to quadratic model. And again, obviously it looks like a line because this data is linear. Let's kind of change the scores we use, 5 times hours. So let's say it takes essentially hours squared plus 440, say 0. So let's say there is no baseline, and what you get from the score, what you get from the exam is basically the square of the hours you work, right? So now, again, you get the nice curve, right? So it tells you that, yeah, the hours times hours, so that's x squared's coefficient is 1, the others are more or less 0. So that's about it for all of the stuff we talked about. It's been more than 2 hours. I'll put chapter markers on this thing so you can jump to wherever you want later on. But I think, although it's a bit long, I think it will be useful later on. If you're kind of confused about something, you can just jump back to this video and kind of maybe see how to move forward. Okay, well, that's it for this video. Thank you.